Hey, welcome back, and in this video I'm going to show you how you can quickly get started with Apache Kafka. Now if you don't know what Apache Kafka is, it's a highly distributed, highly scalable, fault-tolerant event streaming platform, and you can use it for essentially decoupling backend services and do asynchronous message processing and event streaming. Now if you don't know what any of that means, don't worry about it because I'm going to explain that all in a second. Okay, so the first thing we're going to do is we're going to walk through some of the key concepts of what Kafka is and how it works. Now, as I said, it is an event streaming platform or a messaging platform. So if you think about that, what I am trying to do is I'm going to asynchronously process messages. So it's going to be a platform where I'm going to have a message of some sort. It may be an event, it may be a message, doesn't really matter. And I'm going to write that message onto the platform, and then later on something else is going to read that message and then do some processing involved in that. So if we think about that, if I just draw here, maybe on the center here, I'm going to have something that is Kafka, right? So that will be our starting point. So I'll just draw that on the iPad. You can see Kafka. So as I said, there are going to be people who write to the platform, and there are going to be things that read from the platform. So in Kafka terms, writers to Kafka are known as producers. So we'll just write that there. So producer. So anyone who writes to Kafka is a producer. And we'll just draw another one. And as you can imagine, there can be multiple producers of the system. So we'll just write producer, and they are writing to Kafka just like any other message or any other queue or any other sort of stream of some sort. So once messages are written to Kafka, then you're going to have something that is going to be able to read that, and they are the consumers. And so we'll just write that in there, consumer. So that is our sort of key concepts that you've got is producers write to Kafka, consumers read from Kafka. So now that we have an idea of the terms producers and consumers, let's pull back the layers a little bit and look at what's going on in Kafka. And actually the first thing to understand is this concept of a broker. And a broker is really just a server in Kafka terms. And that's the easiest way of thinking about it. A broker is just a server. And actually when we think about this, producers actually talk directly to brokers. So part of the things that brokers have is they have the APIs. So anything that is exposed to the outside world, via things like the REST APIs, etc., then that is exposed via the broker. And that is what the producer talks to. So when a producer wants to send a message into Kafka, it is talking to a broker. So we can sort of draw that on the iPad again. So I can just write producer. And what it's going to do is it's going to send a message. So we'll just write send, and we'll have M that represents message. And then it's going to talk to a broker. Yeah. And then that in Kafka terms, a broker is, just think about it as a server. Now we'll get into scalability of Kafka in a second, but you can pretty much probably guess already that in order to be scalable and also to be fault tolerant, then you're going to have multiple brokers or multiple servers that exist within your Kafka estate, or as Kafka terms like to name it, within your Kafka cluster. And all a Kafka cluster is multiple brokers that reside within the cluster to form the overall Kafka service. So we've got this broker here. At the moment, we've got an individual broker, and this broker is within this Kafka cluster that we said. And therefore, the message has to go somewhere. And to do that, what a broker is writing to is essentially writing to a thing called a topic. Now this is not the best diagram in the world because I ran out of space. I wasn't really thinking of that there. But what it's going to do is it's going to take that message that came in from the producer, and the broker is then going to append it onto a thing called a topic. So I will write append here, and we'll put append M. And then a topic it's really like a big log file. The really nice description of Kafka that I've seen is think about it as like a log file, and therefore when you're appending things or when you're reading from logs, and think of it as like a kind of tail of a log. But we can sort of draw this out. So let's just draw what would look like a kind of a log-based system with kind of slots. And this also could, if you think about it, looks like a bit like a queue there, so that's fine. So I'm gonna put M on my log here. So this is the first item on there, so that's the message, so it's doing an append, and this is on a topic. There we go. So that is, when you hear the word topic, think about it as your log, your message log. Think about it is basically the storage area where messages are being held. So now that you understand that, if you if you think about it the other way, then later on when a consumer wants to read messages, they are just going to read from that topic. They're going to read from that log any messages that have been written. So this is our first point, and then again I'm just going to put another fancy graphic up on the screen there now, which basically shows what we've got. So we have this producer, it sends a message to a broker. A broker is just a service within your cluster, and then the broker is going to append the message into what is known as a topic, and that's where that's going to reside. And once it's on that topic, then a consumer will be able to read that later on, okay? So now that we've got that, we've got producers, we've got consumers, we've got brokers, and we've got topics. Now, as I said, Kafka is a highly scalable platform, and you're going to have multiple brokers, and we're going to look at that in a second. But in order to be both scalable and to be able to be things like fault tolerant, then we need the topics to be scalable and fault tolerant as well. And the way that is achieved is the topic, in some regards, is actually a sort of logical construct. And what we actually have from a physical perspective is what is known as a topic partition. So what do I mean by that? So the topic partition is the thing that resides on the broker. So for a topic, a broker would have a single partition representing that topic. So if I only had one broker, then I would only have one topic. So why is that important? And it's important because partition is essentially the unit of scale for these topics. So that allows me to have things like fault tolerance, and it allows me to have things like scalability, i.e. be able to scale out my topics out to multiple servers to increase throughput. So if I come back to the example that I was showing earlier, where I had a producer sending a message to a broker, in this particular example, because I've not scaled out, I actually only have one broker. And because I only have one broker in my Kafka cluster, then actually I only have one topic partition as it stands, because that is my unit of scale. So if you think about it, the producer is sending a message to the broker, and then the broker is appending the message to a topic partition. Yep. And then of course later on when we look at scaling, then we will be able to introduce more topic partitions as a unit of scale, but also when we look at fault tolerance, more partitions will be able to appear across different brokers. But we'll come on to that slightly later. So for just now, in a single broker world, and a single topic world, then I have a single topic partition. So back to this example, my producer is sending a message, M, to my broker, and my broker is appending a message onto a topic partition. And therefore I have M appearing on that message. And that is how producers work. Pretty simple stuff. Okay, so now that we understand that, let's deep dive a little bit further and look at the Kafka architecture as a whole. So in my previous example, I had one broker in my Kafka cluster, but of course I can have many, many more brokers, many more servers, right? Because I want that ability to scale and have fault tolerance. So this is where this idea of a Kafka cluster comes in. So my Kafka cluster essentially is just something that contains one or more servers or one or more brokers in this particular case. That's all a Kafka cluster is. So now that we get what a Kafka cluster is, let me just draw that out again just to make the architecture sort of come to life a bit. So we've got our producers. So I'm going to write producer 1, producer 2, producer 3 in this sense. And now we understand that we are talking to Kafka clusters. So I'm going to write Kafka cluster here. So we'll just write Kafka cluster. Okay. And then, as I said, a Kafka cluster can have one or more brokers. So we'll just write kind of B1 for broker, B2 for broker, and that could go all the way across to sort of Bn. So we can have multiple brokers. And then, of course, we're going to have our consumers who are going to read from our cluster. So we'll just write that here, consumer, consumer, consumer. Okay, and that is a Kafka cluster. But of course, I need something that can manage that cluster. So something that is going to be responsible for making sure that the brokers are up and running. If the broker fails, then restart the brokers. And how that is run today is with a tool called Zookeeper, which is responsible for keeping the brokers up and running. Now, in future versions of Kafka, then they are trying to get rid of Zookeeper and have a Kafka sort of its own protocol for managing clusters. But for just now, we're using Zookeeper in this particular sense, which is a sort of cluster management piece of software. So if we look at the fancy diagram there, that sort of brings our architecture together, which is this sort of Kafka cluster consisting of brokers, Zookeeper to manage the cluster, and then our producers and our consumers. So if we think about this, in our overall cluster architecture, the broker handles all requests from clients and keeps data replicated within the cluster. And Zookeeper manages the Kafka cluster and its state, i.e. the topics, brokers, and users. So that is the sort of shared responsibilities between the two. So of course, if I'm scaling out my brokers, then I'm also going to need to scale out my Zookeepers as well over time as well, or my Zookeeper instances, because that will be a point of scale. So if I want to have lots and lots of brokers, that's fine, but I can't have a single instance of Zookeeper either. I would need to scale that out and have multiple instances of Zookeeper to manage the cluster. So that, if you think about it, allows me to have scale, and it allows me to have fault tolerance, and we'll deep dive into that a second. From a Zookeeper perspective, you would usually have sort of 3 to 5 Zookeepers in a cluster. You keep the numbers low to conserve overhead, and you always have odd numbers to maintain a majority. So if you think about your Kafka cluster as a whole, if we just come back to that, then I'm going to have somewhere between 3 to 5 Zookeepers instances to manage my cluster as a whole, but my broker, I can have thousands of instances in that, right? That can scale to whatever it needs, because that is going to be running all my topics. But Zookeeper is about 3 to 5, and that's sort of my point of fault tolerance and scale in that sense. Okay, so we understand our Kafka cluster now. It's got brokers, we've got our Zookeepers to manage the cluster. So now that we understand that, the last thing I want to talk about before we crack open the code and actually write some code and get it up and running on our machine is how do these topic partitions scale with brokers? And again, we'll go into that in a little bit more detail later. But the nice way of thinking about this is you are going to have a topic partition per broker. So if I put broker 1 here, and I put broker 2, and I'll have we'll have broker 3 there. Then if you think about it for a second, in order to have something like fault tolerance, I need that partition to get sort of replicated across multiple brokers. So, from a fault tolerance perspective, the minimum sort of number of replicas or copies that you need would be about 3, and that's following the kind of camel in the desert principle. So in this sense, if we took our topic partition, so let's say we had a topic called Chris, and that's our topic partition, and as I said, there's going to be one there. Then in order to have fault tolerance, you would also have a copy of Chris here, which would be your sort of replica. And you would also have it over here as a replica as well. And that means because each broker has a copy of that topic, that then starts to give you fault tolerance replication. So if broker 1 dies, so if we just put an X through that, then broker 2 would be able to pick that up, and or broker 3 would be able to pick that, and they would become what's known as the leader, right? So they would be the one running the cluster. Now, just think about this for a second for that topic, right? Is as soon as you get down to 2, then you are essentially you're gonna sort of, if you lose that one extra node there, then you're not gonna be able to maintain your cluster at that point, because you're going to be running out of nodes to run fault tolerance. So you need to sort of try and maintain 3 there, but you can deal with losing a node, but you certainly can't lose 2 nodes. If you lose 2 nodes, then you can't guarantee your consistency sort of beyond that. So therefore, it's just something to be aware of in that sense, that you do want to have as many sort of brokers kicking around. You do want to maintain a minimum of 3 replicas. We'll look at that when we talk about the settings there. But of course, so you'll have two brokers at that point, and then if we stand up another broker, that's where Zookeeper would come in. It would try and restart that broker, get it back up and running again. Or if you had another broker that was available, then that data could get replicated onto that. So that's kind of how brokers work in that sense. But that gives you that sort of availability side point of view. Okay, so we had this topic and a topic partition, and as we introduce these multiple brokers, then that can be replicated across the multiple brokers, and therefore I could lose a broker and it could have those messages will stay persisted. Now, from a sort of broker perspective for a particular topic, then there's this concept of the leader. And what that means by that is that if you think about the writing of messages to a topic, so I had my sort of messages here, which is sort of M and M1, 2. So if let's say I had a message M1, M2, M3, M4. As I write those messages, because I want to maintain order, M1, M2, M3, M4. So when the consumer comes along and reads those messages, M1, M2, M3, M4, then it wants to be able to read that in order. Now, if you think about that for a second, if I allowed writing on broker 2, broker 3, broker 1 in parallel, then I wouldn't be able to maintain the ordering of these messages, right? Because I could write M1 to broker 1, M2 to broker 3, and M3 to broker 2. Then, depending on the order they got written to the log and then replicated, then that order wouldn't be guaranteed, it wouldn't be consistent. So the way that Kafka maintains that ordering is by essentially saying that for a topic partition, then only one broker can be the leader. And what it means by that is one broker is responsible for writes. So in this sense, when the producer writes to the broker, then it's going to be writing to the lead broker. So in these brokers for that particular topic, so for the Chris topic, there only one of those brokers would be considered as the leader, and it would go to the leader broker, which would then write the message, and then it would get replicated to all the other brokers there. And now that becomes super interesting from an acknowledgement perspective, right? Because then you can start to have settings on the producer to say, what sort of mode do I want to be in for consistency, right? So you could be, or even availability in that sense. So you could then start to decide things like, actually, I want all of the replicas to confirm that they've got that message, and when the messages have been confirmed by all replicas, then at that point I'm going to say the message is written. It could also acknowledge messages by just saying, I only want the leader to confirm the message, or you could just do a fire forget and say, I don't really care if it's written. As soon as I've done the write, told the broker about it, I'm done. I don't really care if it's written to the partition or not. So there's different modes that the producer has. By default, it's all replicas have to acknowledge that they've got the data before you can say back to the producer that it's been written. And that gives you a sort of transactional consistency. But you've got that ability within your client to be able to decide that. I would recommend you keep with the default. There's pretty much not. There's some reasons you might want to do a fire forget, but in general, that sort of default, all replicas acknowledging that they've got the data is probably a good place to be. Okay, so just to kind of recap where we are at the moment. So at the moment, we've got producers, which is cool. We've got our cluster, which is all of our Kafka brokers or servers that we have in our system. So we'll put cluster over here. The producer is writing to a broker. And then we have multiple brokers that could exist all the way up to kind of broker N. And then we have topics. And each broker can have one partition for a particular topic existing on it. So let's say we've got a topic called Chris, and therefore that one of those brokers would be considered as the leader. So anytime that the producer is writing, it would write directly to the leader of the broker. So it would go and talk to the cluster, talk to the brokers and say, okay, I need to know who is the lead broker for topic Chris. And then it would go to broker 1 or broker 2, and then it would do the writes. And then any other broker that is part of that replica set then has that data replicated to other brokers. So that's so in this case for the Chris topic, it could be broker 2 and broker 3, and they would have a copy. So they would be essentially one of the followers in that sense. So and they would have a copy of that data, and therefore if the leader, let's say broker 1, who was a leader, died, then obviously Zookeeper is going to try and spin up a new broker, etc. And then within Kafka, within its protocols, then a new leader would be elected amongst the followers. So the Chris follower, who was a follower, would then become a leader. Zookeeper would then try and spin up another broker for you so that you're maintaining your brokers or get that previous broker back up and running, and therefore you can sort of maintain that replica set. And of course, in order to maintain fault tolerance, you really want to have 3 brokers running, but it can sort of survive running 2 brokers. If you lose more than 2, if you're down to 1 broker, then you can't guarantee the consistency of the data. So and it'll get into a kind of flux. Now, the good news there from a Kafka perspective is that leaders can split for different topics. So let's say I had another topic called Fred, so we'll put that in there. Like the Chris topic, it would have its replicas sitting over here across the brokers. So that, in this case, Fred could be over there, and leaders and followers can switch across different brokers as well. So in the case of Fred, broker 3 could be the leader, but broker 1 could be a follower, and therefore that's really important from a kind of cluster management perspective, because then the load can be split across all the various brokers. So if I've only got 3 brokers, then you can imagine that I'm only going to have 3 replicas anyway. So if I had 3 topics, maybe one would, each different broker would have a different leader for different topics. So it doesn't mean one broker is going to be the leader for every single topic partition that exists. So it'll be evenly distributed across everything. And that way that you're getting most usage out of your cluster. Now, where that really becomes important is if I've got a lot of topics, maybe I've got 1,000 topics, and maybe I've got something like 10,000 servers, then all of those topics are going to switch across all that massive cluster of 10,000, and therefore it's going to be sort of distributed across so that the brokers are not taking too much load. So that you start to get an idea of scale. The more topics that I have, then they're going to move around that cluster, etc. Okay, so as it stands, we've got a pretty good understanding of how brokers work, and we have a pretty good understanding of how Kafka maintains high availability by having replicas of your topic partitions. And that works really well, as you saw, which is that you have more than one copy, 3 copies of your data residing on different brokers throughout your Kafka cluster, and therefore if one broker goes down, then it goes across to one of the other brokers. Now, the problem that you might be thinking at the moment is, how do I ensure that my brokers are not co-located in the same place? And let me explain what I mean for a second. So if I'm in an on-premise data center, I could be in a situation where they're all residing on the same rack, for example, or the same machine even. And if I bring that up into a cloud scenario, so maybe it's something like AWS or Google, then if you think about this concept of cloud availability zones within a region, if you don't know what a cloud availability zone is, think of it as almost equivalent to a data center that it sits really closely to another data center within that region. So if one cloud, so let's take an example, let's take AWS. You may have 3 availability zones, and therefore if you lose an availability zone, then AWS would automatically fail you over to another linked AWS availability zone in that region. So it gives you high availability within that region. Of course, we could get into an argument about multi-region availability and losing an entire region, but that's probably well outside of the scope of this particular video. But let's take this availability zone concept and think about this for brokers within our cluster. What we wouldn't want to do is have brokers residing, right, for a particular topic partition. We wouldn't want those replica topic partitions residing on brokers on the same availability zone, because in that case, if you lost an entire availability zone, what you end up doing is risking the integrity of your cluster, because essentially everything in that zone has gone. Let me explain what I mean for a second. So if we get the iPad out and we just draw this up, so let's imagine we've got 3 availability zones. So I'm going to say, let's call this zone A, and we will have zone B, and we will have zone C, right? And essentially we would want our Kafka cluster to spread across all 3 availability zones. Okay, so that's going to represent our Kafka cluster here. And then what I'm going to do here is I'm going to have 3 brokers. So let's put, we'll have broker 1, and that's going to reside in zone A, and we'll have broker 2, and that's going to reside in zone B, and then broker 3. And that will reside in zone C. Now, if we think about this for a second, I'm going to have a topic partition. Remember, topics is really a logical cluster or a logical construct, and the topic partition is the unit of scale. It's the physical thing. So, and as we described, a topic partition needs to reside on a particular broker, and you can't have the same multiple topic partitions on the same broker. It's one topic partition per broker. So if I had my Chris topic and I had that in on a broker, so I've only got 3 here, so let's put Chris topic here. So we'll call it CT here because I'm being lazy, and then we'll have another one because we're going to have a replica here, CT. And then we'll have another one here, which is CT. Now I'll mark broker 1 as the leader, and we'll mark broker 2 and broker 3 as the replicate. But as you can start to see there, that works well if I've got my split of my brokers and my topic partitions spread evenly across the zones. Now, And by the way, of course, for different topic partitions or different topics, again, as I said before, they don't need to all reside in one zone. In fact, it would be spread across. So if we had another topic, let's have the Jemima topic. And in this case, it could be a replica here, but broker 2 could be the leader for Jemima topic. And broker 2 would be the leader, and then in this case for Jemima topic, this would be a replica or a follower. So if you think about this logically for a second, if I lose zone A completely, I'm going to lose that broker and all of those topic partitions, and one of the other zones would pick it up. So that is a nice spread out scenario that I'd want to maintain, which is my brokers are spread across the zones. So if I lose a zone, I can pick that up. What I wouldn't want to happen is in zone A, I wouldn't want broker 2 residing down here in zone A. That would be, and as well as the partition, that would be a bad scenario, because therefore if I lost zone A, I would lose broker 1 and I would lose this topic partition here, but I would also lose these topic partitions there. So I need to have this evenly spread across my availability zones. So that's the kind of concept there, and how you can achieve that is really simple within Kafka. And again, we'll look at that in one of the other videos when we do the implementations, is you can actually use a function called rack awareness, this configuration setting, and you can just set a thing called broker.rack. And therefore, when you are creating your brokers, so broker 1, broker 2, broker 3, you can set an identifier of some sort which allows you to identify how you want to treat the rack awareness. So in the case of AWS, you would probably set your broker.rack to being aligned to your availability zone. So you might set this to be zone A in this particular case for broker 1, and then for broker 2, so we'll say B1 here. For broker 2, you would set that to be in zone B, and then Kafka will look at the broker.rack setting and then make sure that it doesn't place those brokers anywhere else. It will spread the brokers across the zones, but it will make sure that it aligns to that availability zone that you specify. So that is a really cool way of doing that. So that means that from a replica perspective, then you've got that rack awareness, and you're not going to load any replicas or followers for those partitions in the same zone and risk outage from a particular zone. So that's really cool. Obviously, it opens up a whole set of other scenarios that we're not going to go into, because you're now in a position where producers are, and even consumers, and we'll come on to in a second, where producers may be writing to something that's in a different availability zone. So the producer might be living in a different availability zone from the broker. So there's a lot of complexity that comes in, because that would create latency, and you want it to be really close. So there starts to become a little bit of complexity that's involved, and again, it's outside of the scope of this video, but one of the things that you can do is you can write a little custom routine, a custom selector as such, which allows you to then be able to use the right producer to talk to that's going to reside in an availability zone to allow you to do the right. So there's a whole set of things that you can do around that, but it's quite complicated and probably well outside of the scope of what we're doing here. Okay, so that is rack awareness within Kafka, and I think it's a really cool thing. Okay, so we've got a pretty good idea of how high availability works, and we've got a good idea of how scaling occurs within a cluster for different topics. But what about an individual topic? So as I said before, the topic partition, there's only one version, per broker. Now, and as I said before, order is guaranteed within that partition for a producer. So if I write to my topic partition, and let's say I write M1, M2, M3, M4, M5, and M6, then that order is sort of guaranteed there because I've got one producer who is writing to one broker who's acting as the leader. So in order to maintain that ordering, then if you think about it logically, I can only have one consumer able to read from that topic partition. Yeah. Because if I have multiple consumers who are able to read from that topic partition, then I can't guarantee the order anymore, because consumer 1 could read from M2, consumer 2 could read M3, consumer 4 could read M4. So therefore, they would be reading things and processing things in a different order, and therefore the order can't be maintained. So the only way that you can guarantee that message ordering is by having one consumer, a single consumer, being able to read a topic partition at any time. So that sort of completes that loop. So we have producer and we have consumer. We have the logical topic for producers and consumers, so we can have multiple producers and consumers logically within a topic. But when we bring it down to an individual level, I can have one producer writing to one topic partition and one consumer instance reading from one topic partition at once. But that leads into an obvious problem there, which is that if I have too many messages going on to an individual topic, or topic partition in this case, then I might not be able to keep up with those messages. And that's exactly why partitioning exists in the first place, because partitioning allows you to then say, you know what, I want to be able to have a different way of scaling. So what do I mean by this? So what you would essentially want to be able to do is shard, or have multiple partitions per topic, and then you want a way of separating that out. So what that could mean, if you think about this logically, is that I might have my Chris topic, but then I might want to partition it on something like user ID, or I want to partition it on a system ID or something like that. So some sort of way of being able to distinguish in it. And therefore, by doing partitioning, then messages can be written in order to a particular partition. So what do I mean by that? So let's take a sort of more concrete example. Let's imagine I was writing something like Facebook, for example, or Twitter. So let's imagine I am going to tweet on my Twitter timeline for a second. So I write a tweet, so tweet 1, and then I say hello, and then I go hello world, and then I say walk to the kitchen, ate sandwich, walk back to my room, right? Three tweets. Now I wouldn't want them to be out of order from my user ID, right? You would want in that timeline, walk to kitchen, ate sandwich, walk back to room, in that particular order. Because if it was ate sandwich, walk to kitchen, walk back to room, it wouldn't make sense. So user ID in that sense could be a good logical sort of point of partitioning key. So in that sense, if you think about that, the only order that I can guarantee is order of messages within a partition. And that's how Kafka scales. So in that sense, if I was to partition on something like a user ID, then what it's going to do is actually look at the number of partitions that I've set. So I can say in Kafka how many partitions I want to have for my topic. So maybe I want to have 10 partitions, or maybe I want 20 or 100, it doesn't really matter. But if I've got, say, something like 10 partitions, then that means I could have up to 10 consumer instances. And then what Kafka's going to do is going to look at something like that partition key, let's say user ID. It's going to do a hashing, and then it's going to do a mod, and therefore it would be able to split that out to those 10 partitions. So if that's a user ID, then certain user IDs would for my user ID, it would be guaranteed to a particular partition. So my messages would be in order, but that means that somebody else's, so let's say your Twitter messages, that would also be in order, but it wouldn't necessarily, even though they could be processed out of order. Mine and yours could be processed differently, but that's okay. So if you think about that for a second, we could have a new partition here. So let's call this partition 1. And we have partition 2 for the Chris topic. And then you're going to have my, and essentially I'm going to have message 1 here, message 2 here, message 3 here. And then over here I could have message 1.1, message 1.2, message 1.3, message 1.4. And that is okay from a kind of ordering perspective. So you can only guarantee your order within the partition, and therefore when the producers are writing to this, so we'll just put a producer in here. So when a producer is writing to the cluster, what's going to happen is the producer is going to talk to that broker, and because of the partition key for the topic, so let's say we've got user ID 12345, then it's going to know what partition it's going to go to. So again, similarly, it will talk to the leader for that topic partition. And then once it's talking, it could be talking, so if it was your one, it would be topic partition P2, which could be on broker 3. My tweets could go on topic partition 1, which could be on broker 1. So the producer would be writing to different brokers depending on where that topic partition lives. It'll write the message and then it'll get sort of replicated. So it's something to be aware of. And then similarly, you've got the replication as well. So each topic partition would be replicated to different brokers as well. So if you think about that for a second, that allows massive scale, right? As long as you can partition correctly and you understand what your partitioning keys are going to be, how you're going to do that, and how you specify your topics, then you've got replication, but you've also got massive scale, because as long as you're not worried about the ordering, then you can kind of scale at that point. So that idea of partitioning. If you don't specify a partition key, but you specify a number of partitions, so let's say I want 10 partitions for my Chris topic, then how Kafka will deal with that is it will just round robin, so evenly distribute your messages across the different topics, which is fine for scenarios where you don't care about message ordering. But if you do care about message ordering, such as you want a certain user's tweets to be in the same order, then that's something that you may care about. So that's how partition works. That's how things scale. It's pretty cool stuff, but the key thing that you need to be thinking about is, what order do I want my messages to be in? Okay, now that we understand how ordering of partitions work, and we understand how delivery acknowledgements works in those 3 modes, which is sort of fire and forget, leader acknowledgement, or acknowledgement for all replicas within a set. So now that we understand how all of that works, actually it's probably worth us just understanding how Kafka handles message delivery for a second, because I think it's really important on that acknowledgement message. And then that will open us up into understanding how transactionality works within Kafka. So let me draw this up for a second. So if we just draw here, let's draw here our producer. So we had that there before, yep. And as I said before, what's going to happen here is the first thing that we're going to do is we're going to send a message. So we're going to send our message, which is going to be M1. Yep. And then, as I said, the broker will accept that message. Now, what the broker is going to do at that point is it's going to append a message onto the topic partition. So that's the physical kind of scale thing. So we'll just draw our topic partition here. So topic partition, yeah. And then it's going to put M1 onto our topic partition. Now, what happens at this point is the producer is going to wait for an acknowledgement. So this is we'll put 2 here, which is append M. But what it's going to then expect is this acknowledgement message back from the broker. So in fire and forget mode, it's not going to care, right? As soon as it does that send, it doesn't care if it gets an acknowledgement, so it'll just move on, right? But outside of fire and forget, it's going to wait for this acknowledgement. So let's draw that in here. So the producer is expecting an acknowledgement here of M1. Now, if the producer gets that acknowledgement, it's fine. At that point, it knows that transaction has been committed. That it knows that that message is on that broker. Now, as I said before, if the leader is given an acknowledgement on the right, then as soon as that append occurs, the broker will send the acknowledgement straight away. If, however, if you've got you must acknowledge every replica having a copy, then actually what's also got to occur here is every other topic partition, in your cluster, all the replicas, the followers, will need to do their write. So the write will need to happen here, the write would need to happen here, and once all of the replicas have confirmed that they've done their write, then at that point the broker would send the acknowledgement here. So that's the difference of how that works. Now, what happens if an acknowledgement isn't sent? Well, if an acknowledgement isn't sent, then what's going to happen is the producer is essentially going to resend the message. So it'll just send M1 again. Now, in this particular case, if for whatever reason there is some sort of issue with the broker, maybe it didn't get a chance to send out that acknowledgement message, then you can kind of see that there would be a scenario where you could end up with duplicates, and therefore that M1 message would be written twice. So we've drawn that on the iPad, but what I'm going to do is just show that on a fancy graphic here. It's the exact same thing as we said before. We've got this standard flow where we send a message, goes to the broker, and the broker appends it on the topic partition, and the producer is expecting that acknowledgement message. And again, just as I drew on the iPad a second ago, let's re-show that scenario, how we end up with message duplication. So in this particular scenario, we are sending a message M2 from the producer onto the broker. M2 gets appended after M1. For whatever reason, that acknowledgement message didn't come back. So M2, no acknowledgement message. So the producer does the retry on M2, and then eventually it appends M2, and therefore you end up with M2 appearing twice, and then the acknowledgement happens for M2. So there's a lot that we've got going on there, right? We now understand how the acknowledgement happens within Kafka. We understand also how the various acknowledgement modes for the various brokers and replicas, so fire and forget, leader acknowledgement, or all replicas acknowledging. But we also now understand how duplication could occur as well, which is if you don't get that acknowledgement coming across, then you could end up with double messages on the queue. Now, why is that important? Because actually there's some cases where you wouldn't want duplication, and that's probably a really important thing. So maybe if you're doing something that is financial transactions, then that would be a scenario where you wouldn't do duplication. So a good example is, I think, Uber. They run their advertising, their real-time pricing type things off of Kafka. So in those scenarios, they wouldn't want to double charge people their advertising, for example. So therefore, they would want to get rid of that message duplication. Somebody like banks, for example, or if you're sort of replicating logs, database logs using for Kafka, then another scenario where you wouldn't want duplicates. But maybe something like if you're running a social network, maybe it's a Twitter or a Facebook or something like that, and you're doing likes, maybe you don't care if you get a bit of duplication there. Maybe you can deal with that because you're not worrying about consistency so much in that sense. So in that case, you know what, it's okay. I can deal with a bit of message loss, I can deal with a bit of duplication. But in those financial situations, what you could do is do a transaction, and And again, I've got a little bit of code showing on the screen. We will do that in one of the other videos where we code up in Kafka JS, but I just want you to kind of be aware from a kind of transaction point of view. What you can do is say, actually, I'm going to configure Kafka so that I'm going to be having exactly one message on the queue when I do my production. And how you would do that is essentially you would need to, there's a couple of settings that you would set, which is the max in-flight request setting would be set to 1 so that you've not got multiple in-flight requests going on. You would have to set the idempotent flag there to being true, so that's what's going to enable that. And then the last thing that you would do in this case is you would have this concept of a transaction. So when the producer is going to send that message, so when we do that send M1, then you're going to wrap that in a transaction, so when it's doing the send, and then finally you're going to send this sort of commit message at the end once you've got the acknowledgement back. So you get into this sort of two-phase commit scenario, and again, that's something that is completely supported by Kafka, and then that means that you don't get those duplicates at that point. So you would be in this scenario where, because you've wrapped the transaction around this, you would just write M1 and you would have exactly once delivered. Now, of course, the downside of the transactional approach is you're obviously there's a little bit more processing that Kafka's going to have to do, and therefore that will slow down your throughput a little bit as well. So there's a trade-off of performance against that sort of level of transaction consistency. Okay, so now we've got a pretty thorough understanding of how Kafka works, how Kafka clusters work, how producers work, what topics are, what topic partitions are. I really want to sort of round this off now with a deep dive on how consumers work. And again, the simple way of thinking about this is consumers are really just the opposite of producers. And okay, so let's draw this out on the iPad again. So if you remember, we have a producer, we'll call that P, and that is going to be writing to the broker, which is B, and the broker is going to write to the topic partition. Okay. And we will draw that here. This is everything within my broker, and then we'll call this broker 1, and then as you remember here, we have sort of broker 2, and then we'll have sort of broker N, and then we've got this sort of alignment of partitions like this. Yeah. Now, if we think about this for a second, what I'm really wanting is I'm going to have a consumer, in the same way I've got a producer writing to a broker and it goes onto a topic partition. What I want to happen is I'm going to have a consumer that is going to be reading from this. So here is my consumer, and we'll call that C1 for consumer. Okay, now that's cool, but there is some rules of the road, right? Which is consumers are assigned to a topic partition. So only one consumer can read messages from a topic partition at any time. And let's just think about that logically for a second, because remember, topic partitions are a unit of scale. If I had consumers that were able to read from different topic partitions, yeah, then I'm going to have another ordering of message problem, right? Because consumer 1 could read from this message here, consumer 2 reads, consumer 1 and consumer 2 is going to get in the way of each other. So consumer 1 reads message 1 here, consumer 2 tries to read consumer message 2, consumer 3 tries to read message 3. It's just chaos, right? They're all trying to keep in sync and figure out who's reading from what. So in this sense, what actually happens is only a single consumer instance can read from a single topic partition. Now that might seem inefficient, but what actually that is doing is allowing us on the consumer side to maintain that ordering of message, allows us fast throughput going through, and it allows you to basically get that performance and availability and consistency all coming from that consumer instance. So a consumer can only read from one topic partition at a time. then how do we scale our consumers? And this is where the concept of consumer groups come in. So in Kafka, you would specify your consumers to reside as part of a consumer group. So let me draw out what that means here. So I'm going to introduce a consumer group here. So a consumer group is really a group of consumers that are there to perform a single task and scale and distribute that across all consumers within that group. So let me draw that out, what I mean. So let's have a consumer group here, and it could be something that is processing bookings, or it could be something that is processing likes, or it could be processing transactions, doesn't really matter. And let's say I'm going to have 5 consumers within my group here. So we'll have C1, C2, C3, C4, and C5. Now let's now look at how this looks from a kind of topic partition perspective. So I'm going to introduce back my Chris topic. So we are going to have, let's say we will have topic, the Chris topic, and we are going to have partition 1. So we're going to have Chris topic, partition 1, and that's going to reside on broker 1. And then we'll have topic 2, so Chris topic again here, and that will be on broker 2. So in these cases, if you think about this for a second, only one consumer can read from a topic partition any one time. So in this case, let's imagine consumer 1 is reading from Chris topic 1, and therefore that's fine. And then from a scaling perspective, if I want to read data and process data from Chris topic 2, then consumer 2 can pick that up. So that's how I start to scale, right? And that's why partition is important, because if I only had one topic partition, if Chris topic only had one partition, only one consumer would be able to read from that, and therefore I would be, from a scalability and throughput perspective, could only perform as fast as the number of consumers that I've got, i.e. consumer 1. So in order to increase my throughput, I can therefore increase the number of consumers in a consumer group, and that is my scaling point for read throughput. So in this case, I can double the amount of messages I can process because I've got 2 partitions. Now, if you think about this for a second, I want to scale a bit more. So I will introduce broker 3, and we have consumer topic 3. So, and again, at that point, consumer 3 can pick that up. So now I've got 3, and it's the same way as we were talking about for the right element with producers. Our unit scale is consumers, and therefore I've got 3 there. Now that means that logically, if you think about this from the iPad perspective, I can only there's no point me having instances beyond the number of partitions that I have, right? The maximum, these other consumers are just going to sit idle, right? Because they've got no work to process for that topic, right? It's what can it do, right? It's 3 instances, and you're going to look at 3 topics. So if I want to scale further, then I need to introduce more partitions, more topic partitions, and therefore more consumer instances can pick that up. So that is a starvation of work thing. So there is no point having more instances than topic partitions, because they won't be able to scale. So that is how topic partitions work, and that's how consumer groups. And of course, as you saw from a producer perspective, I can add more partitions at any time, or I could scale up and introduce more instances, right? Now, there is a link here. As you see, consumer 1 is linked to topic partition 1. Now, what if I lose a consumer instance for whatever reason? Of course, I could have the opposite scenario to this, where I may have a topic. Maybe I've got 3 partitions, 2, 3, and then I may have only got 2 consumer instances within my group, and that may mean that I have double allocation in that sense. So consumer 1 could be handling Chris topic 1 and 2, whereas consumer 2 could be dealing with Chris topic 3. And then of course, so that means consumer instance 1 is maybe a little bit overloaded in comparison to consumer instance 2. So I may decide to try and increase my scale, and I may introduce another instance, C3, and therefore at that point the consumer group would rebalance the cluster, and then and essentially assign that work to consumer instance 3. So in this case, you would get this. Of course, rebalancing. So at that point, I'm pretty good because I've now got 3 instances and I can increase my throughput. But of course, there's a little bit of work happens to reallocate consumer instances. So I want to know what my consumer instances are a little bit in advance, because if I start scaling up and down those consumer instances, then there's a little bit of work that the consumer group needs to do to rebalance the work across all the consumer instances, and therefore there's going to be a delay. It will stop processing the messages, and that will cause you a little bit of delay in processing. So you want to be a little bit thoughtful about that. But as you can see, the mechanism exists both to kind of scale up and down your consumer instances, and then have that sort of that tying to partitions. So that's kind of how consumer groups work. One of the things that you want to be aware of, previously we talked about rack awareness and producers, right into your broker, and then the brokers being spread across the various availability zones, and then the topic partitions being spread across those availability zones as well, so that the data isn't residing in one area. As I said, the problem with that scenario is that you've got latency across multiple data centers, and therefore one of the things that's pretty cool about consumer groups and consumer instances is you can also align a consumer instance to an availability zone as well. And there's a setting called client.rack, and then you can say this client resides in this availability zone, and then what will happen is the consumer group will align your consumer instances to being close to the broker's availability zone that it resides in, and therefore that's pretty cool. So if I've got a topic partition in availability zone A, then consumer instances that live in availability zone A will read from that as well, rather than trying to have cross communication. Of course, there's more complexity than that, but again, it's something useful to kind of be aware of. That leads us into another thing to be aware of as well is, as I said, producers can only write to the leader of a topic partition for a topic. However, the nice thing about consumer instances is, of course, it used to be in Kafka they had to read from leaders as well, but actually they have the ability to read from followers, so they don't necessarily need to read from the leader, they can read from followers as well. And that's really useful because that gives you scale, but it also means in that availability zone scenario you can configure Kafka so that it reads from the closest follower, the closest replica, so that I can avoid cross data center traffic. So I think that's something super cool there as well. Okay, so that's how consumer groups work. That is my overview of Kafka, a little bit of a long one, but I'm hoping that you really understand those topics. And therefore in the next video, what I'm gonna do is we will get Kafka.js out, and we will actually start interacting with Kafka, get it up and running on a server, and write some topics, etc. Anyway, I hope this has been useful, and we'll catch you in the next video.